Now let us put the value of this lambda, that is q, divided by pi r. This is a half circle, so it will be pi r square into 2. This r square we can cancel. We will get 2q by pi. I think so I have not written the direction. This was in j cap direction and this was in I cap direction. So what is left is in j cap direction. The same answer can be also obtained by applying the center of mass concept. If you consider this semicircle with positive charge distribution, see, when we make this a semicircle, the origin will shift somewhere here. That means we can find the position of this center of mass. It will have shifted this much. If we know directly the value of center of mass, it will be same. It will be 2r by pi. It will shift by 2r by pi. So we'll directly get the dipole moment if we know the position of center of mass. So center of mass concept also can be applied to find the dipole moment in some cases. In cases where the charge distribution is symmetrical, the charge is at the same distance from every point. Here we can apply the center of mass concept to find the dipole moment. Now let us look at how to find the potential and the electric field of the electric dipole at a point. Let us consider this point to be point P. This is a dipole having negative and positive charge. This is the origin of the system. Let us consider this distance as L and this also as small l. This will make our calculations a little bit easier. Let us say that this negative charge, from this negative charge, the point is at r minus vector, and from this positive charge, this point P is at r plus vector. From the origin of from the midpoint of this positive and negative charges, the point is at a distance r. So let us first find the potential, and by using the relation electric field is equal to negative gradient of potential, we can easily find the electric field. So first let us write this r negative, or let us first write the r positive by using the vector law of addition. You can see that this r positive, this L here we can see it is in this direction and this is in this direction. If we consider this midpoint to be the origin of the dipole system, so we can write this r plus vector plus L vector here will give us this r vector. So we can write this r vector magnitude as equal to square root of r square plus L square plus minus 2rl cos theta. Here we are using the law of vector addition, where we get the magnitude as a square plus b square minus 2ab cos theta. Now the same thing we will try to apply for this negative r. So for negative r, if you see, for r negative, what we will get is r square plus l square, again 2rl cos of pi minus theta, because now this angle here will be pi minus theta. This angle here will be pi minus theta. So pi minus theta means we are going to get minus sine theta. So this will make it, sorry, minus cos theta. So we'll get 2rl cos of theta. This will be magnitude of this negative r. So we know the definition of potential. This potential will be kq by r plus minus kq by r negative. So this kq is common in both the cases. We will get 1 upon r plus minus 1 upon r negative. So let us put the values of this r plus and r negative. We will have kq, r negative, r positive is square root of r square plus l square minus 2rl cos theta, minus we have square root of r square plus l square plus 2rl cos of theta. Now let us take this r square common from these both denominators. If I take here r square common, let us write here 1 by r square common. If we take and square root is there, square root and r square will cancel and we will get 1 divided by 1 plus this will be l square by r square minus 2 l by r. We have divided each term by r square. This will be cos of theta raised to 1 by 2, and minus here also will take 1 by r common outside. In the denominator we will get again 1 plus l square by r square plus 2l divided by r and cos of theta raised to 1 by 2. So we can take this r outside. We'll get k cube by r, and now here we can apply the binomial expansion, and we know if we consider for r which is at a larger distance from this L, we know that this L by R is going to be a small term. This L by R is going to be a small term, and L square by R square is going to be very, very small. Very, very small than 1. So we can ignore this L square by R square. Further, we can apply the binomial expansion to this. So k cube by r, we have in the bracket, we will take this in numerator now, 1 minus 2l by r raised to minus 1 by 2, and minus 1 plus 2l. Here I have not written cos theta. Cos theta will be there, minus 1 by 2 and 2l by r cos theta minus 1 by 2. We will apply the binomial expansion here and we'll consider only the first term. If we apply the binomial expansion and consider only the first term, what we are going to get is this negative will now be positive 2LR. It will be divided by 2. We have power 1 by 2. So it will be divided by 2 cos theta minus where we have plus, we will get minus 2LR divided by 2 cos of theta. We have applied the binomial expansion. So we will get 1 plus this kq by r will be constant outside. We'll get L by r cos theta minus 1, minus into minus will become plus L by r cos theta minus 1 plus 1 will cancel. We will get kq will get 2 times of this L by r cos theta. Here we have another r, so we'll get k by r square. Now this ql is nothing but dipole moment, magnitude of the dipole moment, and this is cos theta. This will be the potential at any point due to the dipole. Now from this we can easily derive equation for the electric field. By using the relation electric field is equal to negative gradient of the potential, negative gradient of the potential. So let us apply this. Let us take the negative sign outside. We will have del by del r of v. I am using the cylindrical coordinate system because here we have considered r and theta, plus 1 by r. Again we have del v by del theta plus del v by del z. Okay, let us put the values here. We have kp cos theta by r square. So in the first term, cos theta can be taken outside. Kp will be constant in each and every term, so let us take it outside. We'll have del by del r. We have 1 by r, so let us write r raised to minus 1 here. Plus 1 by r. Here we can take r constant and we'll be differentiating cos theta. The last term everything will be constant and we will get 0. We'll get 0 here. So minus kp. Here we have cos theta, r raised to minus 1, we'll get minus 1 here. R square plus 1 by r square cos theta, we will get minus sin theta. Okay, I think so I have made a mistake. We have r square, not r raised to minus 1. So instead of r square we'll get r cube here. I hope you have understood what mistake I have made. Instead of taking r raised to minus 2, I had taken r raised to minus 1. So we'll get everywhere r cube. So now we can multiply this kp or bring this r cube outside. Minus sign is common, we can take that outside, it will become plus, and we will have, see I have not given the direction, this will be in r cap direction, this will be in theta cap direction, and this will be in z cap direction. So we have here r cap, and this will be in theta cap direction, this is r cap direction, this is theta cap direction. So finally we'll have kp divided by r cube. That means here we are going to get one more thing, is here we are going to get minus 2. So we'll get 2 cos theta r cap plus sin theta theta cap. This will be the equation of electric field at any point. So in this part we have seen the equation for potential, which is kp divided by r square cos theta, and for electric field we have found out by using the relation E is equal to negative gradient of V. Okay, now let us see the electric field at some important points. Okay, first is the electric field at the axial point. Now let us take 2 points that are in opposite direction with respect to this origin. Now the origin for a dipole, that is positive and negative charge, will be at the center of this negative and positive charges. If we consider the x and y axis, you can see that A is present on the positive I cap direction, whereas B is present in the negative I cap direction. So here at point A, if we apply the equation for electric field which we have derived, which is Kp by r cube, we have 2 cos theta r cap plus sin theta theta cap. For point A, as you can see, the r cap will be in this direction, and the theta for A will be 0. For A, theta will be equal to 0. So what we are going to get is electric field will be equal to Kp cos theta will be 1, so we'll get 2 Kp by r cube in r cap direction. So at point A, the electric field is in this direction. We can say in I cap, positive I cap direction. For point B, theta will be pi, because see, where is this B? B is in opposite direction, so the angle will be pi. So if we put this value, we will get electric field is equal to now cos of pi, that means we are going to get minus 1, so this will be minus Kp 2 Kp by r cube in negative r cap direction. But this negative r cap direction means again it will be directed in along the positive x-axis. And what is the direction of the dipole? The direction of the dipole, if you see, is also in the same direction. Dipole is also directed in the same direction. So along the axis, at any point the electric field will be in the same direction as that of the dipole moment. So this is an important result that we have obtained, which we can use for solving problems. Okay, let us see the second case. In the second case will be in the second case, okay, we'll be taking the point at the perpendicular bisector. So this is our origin and this is the perpendicular. Let us say the point P is at the perpendicular bisector. Okay, now see here the dipole moment is along this side. The angle with this position vector is 90. So if we apply E is equal to Kp by r cube 2 cos theta r cap plus sin theta theta cap, this term is going to become 0. What will be left is just Kp by r cube in theta cap direction. Now what is this theta cap direction? See, at the point P, if we take the r cap direction, the r cap direction is this is the r cap direction. Theta cap direction or the theta direction is perpendicular to this r cap direction. We are taking in anti-clockwise direction, so this will be the perpendicular direction of the theta cap. So the electric field here will be in theta cap direction. That means electric field will be in this direction. As you can see, the electric field will be anti-parallel to the dipole moment. You can consider the point on this side also. So you will get in again anti-parallel direction, the electric field will be in this direction. So at the perpendicular bisector, if you consider any point, the electric field will be in anti-parallel direction. Now let us see how this helps us to solve some problems. Let us consider two dipoles P1 and P2 of equal magnitude, some P, and we want to find what is the electric field at this point A. The distance between the dipole is small d and the distance from the second dipole to the point is x. Now the electric field we know at the axial points. This is A is an axial point. Due to P1 will be in the same direction and due to P2 will be also in the same direction, that is E2. So the net electric field here will be just the addition of E1 plus E2. And for axial points we have seen that the electric field is Kp divided by r cube, 2 Kp divided by r cube. So we can just put these values, Kp by r cube P1 and 2 Kp by r cube. Now P1 and P2 are same, so we'll get 4 Kp by, sorry, we have not considered the directions. So 2 Kp 1, this r cube, this distance for P1 is d plus x, or we'll write x plus d cube. For P2 it is just x. We can take this 2 Kp outside the bracket, as both are of same magnitude, and inside the bracket we'll get this. From here we can take this x cube as common outside what will be left inside will be 1 plus d by x raised to minus 3 we have taken in the numerator and plus 1. For this we can apply binomial expansion. Again, considering that this distance x will be very large as compared to the distance between the charges, so we'll get 1 minus 3d by x so this will be 2 kp inside the bracket we'll get 2 minus 3d by x. Okay, if required we can solve this further, otherwise we can leave it here. Okay, now let us look at the next problem. In this next problem we have this point A. Again, it is in between these two dipole moments. Now see, we can for P it is at perpendicular bisector, and for this second P also it is at the perpendicular bisector. Okay, so what we can do is we want E is equal to Kp by r cube. It is at the, in both the cases it is at the perpendicular bisector. Or what we can do is we can find the resultant of these two dipoles. One dipole is here, another dipole is here. The resultant will be in this direction. This is the resultant dipole. The magnitude of the resultant dipole will be 2 root of p root of 2. So we can just use the, for the resultant dipole, if we consider this is the resultant dipole, the electric field will be for axial points. That means it will be in the same direction as that resultant dipole. So electric field, we can use the equation for axial point, that is 2 k p. In place of p we can write p root 2 and divided by r cube. If required we can find the magnitude of r cube and write in the answer, or we can write kp 2 root 2 divided by r cube. So knowing the point whether it is axial or at the perpendicular bisector will help us solve lot of problems. Okay, now let us see what is the next point. Let us derive this electric field and potential in coordinate independent form. What do we mean by coordinate independent form? We have got electric field which is equal to in r cap and theta cap direction. But many a times they will ask us to find the electric field, let us say at this point A, and we will be given the x, y and z coordinates. That means in I cap, j cap and k cap direction. So we will not be able to use directly that formula. So now we will try to derive the equation of electric field and potential in coordinate independent form. For that, let us understand this. We have r cap in this direction, and we have seen that theta cap will be in perpendicular direction to this r cap. This is the direction of theta cap. And we know the direction of the dipole moment is in this direction, from negative to positive. Okay, let me draw the dipole moment at this point. This is the direction of dipole. So we can and r cap, if we get, is in this direction. This is the direction of r cap, and we can say this is the opposite direction to theta cap. We can write minus theta cap here. Now this angle theta and this angle will be also theta. So we can represent this p vector. We can represent this p vector as p cos theta in, this is in r cap direction, and minus p sin theta in theta cap direction. So we have written the dipole moment which was just in I cap direction into r cap and theta cap direction. Now this will help us convert the electric field which is in r cap and theta cap direction in coordinate independent form. Okay, so let us take this p vector which is now in r cap and theta cap direction, sin theta into theta cap. Okay, from this we can write vector p dot r cap. If we take a dot product of vector p and r cap, what we are going to get is only p cos theta. Sin theta, theta cap will become 0. Also from this equation we can write p sin theta, theta cap equals to p cos theta r cap minus this p vector. Okay, now this will help us convert the electric field. First we'll convert the potential which is kp cos theta divided by r square. Now we can replace this p cos theta term by k vector p into r cap divided by r square. We can also further write this as k p vector, replacing this r cap by r vector divided by magnitude of r, that means this will become r cube. We can replace this r vector by r divided by vector r divided by magnitude of r, because many times will be given the position of that point. Same way we can convert the electric field which is kp by r cube. We have 2p cos theta r cap plus we have 2 cos theta, will multiply this p inside, so we'll get 2p cos theta and p sin theta theta cap. We have already created substitutions for this, so we'll have k divided by r cube. 2 p cos theta can be written as p into r cap p dot r cap into r cap, and sin theta we have found the substitution p cos theta r cap minus p vector p cos theta r cap minus this p vector. Again we can write this, we'll have same outside k by r cube. This will be 2 p vector r cap vector into r cap vector p cos theta. Again we can replace by p dot r cap into r cap minus p vector. We can add these two terms, we will get k by r cube 3 into p vector r cap vector into r cap minus this p vector. Now this is equation of electric field in coordinate independent form. Now let us look at an example how this helps us solve some problems. Okay, now see here, they have given the dipole moment in I cap direction, and the electric field they have asked at this point 1 comma 1. I have taken the points so that the calculation becomes a little bit easier, but it can be applied to any situation. So we'll be using the coordinate independent form of the electric field, because uh, we cannot use r cap and theta cap. The position of vector A. The position of vector A we can write as I cap plus 1 I cap. We have 1 plus 1 j cap plus 0 k cap. That means we have just I cap plus j cap. Now we can write the equation k by r cube. We have 3 times, this is the r vector, we have 3 times p vector into r cap. We'll be converting this r cap into r vector, so we can put the position of that points. We'll have r cap divided by r. Outside also we have r cap. We'll write r vector divided by r minus p vector, that is p dot I cap. So we'll get k by r cube 3. Now p vector is p dot I cap. We have a dot product with this I cap plus j cap, and outside this again we have I cap plus j cap. This whole is divided by r square minus p naught I cap we have. Now this is a dot product, so only I cap will multiply, and we will get k by r cube. Let us multiply. We'll get 3 p naught. We'll get a scalar, that is 3 p naught. Outside the bracket again we have I cap and j cap divided by r square minus p naught I cap. I think so. I think so. Here we have not written the whole form. Yes, we have only p vector, so it will be p naught I cap. So let us multiply this. We'll get 3 p naught I cap plus 3 p naught j cap divided by r square minus p naught I cap. Okay, the magnitude of r will be 1 square plus 1 square, that means we'll get root 2, and r square we can write as 2. R cube also we'll try to find. R cube will be 2 raised to 3 by 2. 2 raised to 3 by 2. So let us put these values. So electric field will be k divided by r cube. That means 2 raised to 3 by 2. Inside the bracket we have p naught I cap plus p naught j cap divided by r square. That means 2 minus p naught I cap. Now we can solve this. We'll get p naught I cap plus p naught j cap minus 2 p naught I cap. This 2 we will take outside, so we'll get uh, 2 raised to, okay, that means we'll have to add this. We will get 5 by 2, 2 raised to 5 by 2. uh, the final answer we can write k divided by 2 raised to 5 by 2 p naught j cap minus p naught I cap. So this will help us find the electric field in cases where the point is given in Cartesian coordinate system. Okay, let us look at the next point, which is a symptotic variation of electric field and potential at a very large distance compared to the distance between the charges. For example, if I consider a collection of charges which are either positive or negative, that means what I am saying is Q net is not equal to 0. And you consider a distance which is very large as compared to the distances between the charges. Here you will get electric field which will be of a point charge, and electric field will be inversely proportional to r square, and potential will be inversely proportional to r. Now we have used these formulas kp by r square and kp by r. But if a dipole is present, or in the collection of the charges if dipole is present, that means q net will be equal to 0 plus minus charges will be there. But let us say p net, or the net dipole moment, is not equal to 0. In these cases the electric field will be inversely proportional to the distance. We are considering distance from the point, and potential will be proportional to r square, as we have seen in the derivation of electric field and potential. We have got kp by r cube and kp by r square. But if from the collection of the charges we get both the things 0, q net is also 0 and p net is also 0, then electric field will be inversely proportional to r raised to 4, and potential will be inversely proportional to r raised to q. In the previous case, in the second case, this was a dipole. We can represent all this collection of charges by a single negative and a positive charge. Same way, in the first case, we can approximate or represent them at a large distance as a single positive or negative charge. In these cases, in the third case, it is a quadrupole. It is a quadrupole. That means two dipoles are present. Okay, this will help us solve lot of questions. For example, see the next problem. In the next problem, we can see the net. They have asked us the variation of the potential and the electric field. We can see the net charge is 0. We have also understood how to find out the net dipole is 0 or not. We can take the origin anywhere. We have taken at the center of the square. If we go in opposite direction, are we getting the same type of charges? Yes, we are getting positive charges here, and if I go in this direction, again I go in opposite direction, I will get negative charges. That means here the dipole moment is also 0. In this case, we have learned that potential will vary with r cube and electric field will vary with r raised to 4. So configuration of the charges will be given and you will be asked the variation of electric field and potential at large distances. We are talking about large distances from this configuration of charges. So we can see whether the net charge is 0 or not, and whether the net dipole moment is 0 or not, and find out how the potential and the electric field will vary. So here we complete the concept of electric dipole. I hope you have understood all the points from this chapter. Try to solve the problems in the assignments. Thank you.